Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. We're doing Math 361, a history of mathematics. 1.2 is basically going to be types of real numbers. Specifically, this lecture, what we're going to do is quickly describe the different kinds of sets of numbers. We've been done in the lectures, we've done background on what set notation is and the basic union and intersection operations and subsets, etc. So I'm going to talk about those freely here, but we'll describe the different sets of real numbers, starting from the positive whole numbers, and then we'll give a way of manipulating and adding with fractions and getting the decimal representation of those guys, and then some of the more horrible irrational numbers. Let's get to it. All right, so these are the kinds of numbers that we have, real numbers specifically. We're going to have, starting off with counting and getting the abstract concept of one thing or two things and giving this symbolization in decimal notation specifically. We're going to have positive integers denoted Z plus. The natural numbers add 0, so this is basically the union of the set 0 and the positive integers, because every natural number is either 0 or a positive integer. The natural numbers add the negatives, so what do I add to 1 to get 0? I add -1, so these things, when I add them together, give me nothing, and so I get the integers. We're using Z for, in German, Zahlen is the word for integer or number. So the next thing that we're going to do is look at ratios. Sharing says that we don't get the whole pie, we get a fraction of the pie or a ratio of this pie. So we're going to get quotients of integers, so the Q, and we're going to call these, classically now historically, we're going to call these the rational ones, which have an infinite repeating decimal expansion. So I can express this in a finite amount using a bar. There's still infinitely many repetitions of everything, but the irrational ones are going to be the ones that have an infinite non-repeating decimal expansion, like pi, 3.141592653587, I don't know, dot, dot, dot. It's never going to end. And so finally, what we can say is the real numbers, or the set of all reals, is the union of all rational numbers and irrational numbers, and the rationals and irrationals have nothing in common, so they're the empty set, their intersection. You're a rational number if and only if you have, what we're going to show is you're a rational number if and only if you have a repeating decimal expansion. So then we ask, are there numbers that have a non-repeating expansion? Yes, there are. And so every number can either have a repeating decimal expansion or a non-repeating expansion, and you can't both have a repeating and a non-repeating decimal expansion. Let's get into that. All right, next we'll recap decimal notation. The decimal notation using base 10, we saw already we can do this in any base we want when b is larger than 2, larger than or equal to 2. Starting with binary all the way up to what we're going to call decimal notation. We're now going to fix decimal notation because this is what everybody in the world uses pretty well. And so for all integers, now we want to know, how do I represent every real number with a decimal notation? And it turns out there will be a fancy theorem, we'll probably list it in the next one scene or whatever, but it'll just say that every number has a decimal representation, and then you're rational if and only if that decimal representation repeats, and then we can get at access to these numbers called irrational numbers, which have an infinite non-repeating decimal expansion. So to start off with, for integers, for the first three sets, positive integers or with 0 natural numbers or with negatives, we're going to have this decimal notation, which is a positional system, which gives us powers of 10, and then we take our digits. Remember where these decays, I forgot all the decays, but di for every I is in the set 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I can still count good. These are the decimal digits. So once I have these decimal digits, I represent any positive integer or 0 or a negative integer. Just tack on a negative in that decimal representation. I now have a way to represent all integers. Now what I want is, I want to know how to represent rational numbers with this decimal notation and irrational numbers with this decimal notation. Then I have a way of representing every real number with a decimal notation. For rationals and irrationals, we're going to need the decimal point, which indicates when the powers of 10 specifically become negative. So now, when we have this representation, the decimal point indicates the fact that right here is we go from 0 to -1, -2, -3, and now we're using the exponents can be all of the integers, not just the positive integers or 0. Let's get at the representation for rational numbers first. All right, these two theorems are, theorem 1 specifically, I'm not going to prove them, they're in the lecture notes for completeness, and I'm going to show this one by rote. Basically, I'm just going to show you both versions with a fraction. I'm going to convert it to a decimal notation. If you give me a repeating decimal notation, I will find its fractional form. So we'll go both ways. Essentially, the theorem says that you can do that for all rational numbers, if and only if. Every real number R has a unique decimal representation. So that says two things, existence and uniqueness. First of all, there is one representation for every number, and there isn't more than one that's unique. And theorem 2, now what we want is, because now I know every real number has a decimal expansion, I want to know whether that real number has a repeating decimal expansion or a non-repeating decimal expansion. Turns out you're rational if and only if you have a repeating decimal expansion. And then we can now ask, do irrational numbers exist in the form of, are there numbers that have an infinite non-repeating decimal expansion? The answer is resoundingly yes, yes there are, and they're a nightmare. And we're going to approximate their decimal expansions with rational decimal expansions. We'll get into that next. First of all, example 1, how do I convert 4/7 into a repeating decimal expansion? Let's do that first. I first want to list the multiples of 7. This makes we're going to use long division. This is going to make it a whole lot easier. So 7, 14, 21, 28, 35, 42, 49, 56, 63. And then I can write times 1, times 2, times 3, times 4, times 5, times 6, times 7, times 8, times 9. I now want to do this. I'm dividing 7 into 4, but I'm just going to write 0.0000 is the trick. I write a decimal point and then a whole bunch of zeros. The first one they start off, usually they skip this, but I'll do it anyways. Technically there's a times 0. How many times does 7 go into 4? No times. What's 7 times 0? 0. I subtract, I get 4. I bring a 0 down. I have 40. Now I ask myself, what's the closest multiple of 7 that doesn't go over 40? Well, when I list them, I was hiding them because this is the game that nobody ever showed you. You want to list these first, especially when I'm dividing 17 or 173 into some other horribly large number. I want to list the multiples of 17 or the multiples of 173 so I don't have to play this game. I can do it a whole lot faster. It's immediately going to be this one. 35 is under 40. 42 is too much, so this is going to have to be a 5. I already know what the outcome is also because I already wrote them down. 35. I subtract, I get 5, bring another 0 down. 50 is going to be 49. I subtract, I get 1, bring it down, I get 10. 10 will be 7. 7 is going to be, subtract, I get 30. Bring the 0 down. Oh, I didn't write my numbers down. So then this would be 5, 7, 1. Then we're going to get 30. 30 is going to be a 4, which is 28. Minus, I get a 2, bring a 0 down. 20 will be a 2. So I write the 2 up here, and I'm going to get 14. I subtract, I get 6, bring the 60 down. Bring the 0 down, I get 60. What's it going to be? It will be an 8, which is 56. I subtract, I get a 4, and oh, there it is. How do I know when I can stop? Just keep doing this, and you'll notice you have a repeating pattern. But as soon as I get the same remainder in this process, I know I have the repeating pattern. Therefore, this says that the fractional number 4/7, the ratio of those two positive integers, is in fact equal to, in decimal notation, 0 times 5. Oh, I didn't write the 8 out. 5, 7, 1, 4, 2, 8, repeating. And what that really means is 0.571428, 571428, 571428, dot, 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 over and over and over again. That chunk of 6 should be there over and over, repeating indefinitely, and we use the bar as the notation. So this just did essentially the by rote version of the first half of the proof. If you're a rational number, which means you're the ratio of two integers, then you do have a repeating decimal expansion. Now let's do an example the other way. What happens when I'm given a repeating decimal expansion? How do I know that 0.6 repeating is the fraction 2/3 in lowest form? Let's do that. All right, now what we want to do is convert 0.6 or 0.6666666. There's infinitely many 6's there. We want to convert that into, how do I know this is a fractional form and what am I going to do? Have you seen this before? Everyone's seen the long division version, I'm hoping, but this was the new one. what we're going to do is we're going to call it x, this thing. Then we're going to create two numbers from x that have the same repeating pattern. Then we can subtract them and get rid of that repeating pattern. That's going to be the clever idea. What? Well, I'm going to let x equal 0.6 repeating, which is actually equal to 0.66. There's infinitely many of these. What I want to now do with that is, if we multiply both sides by 10, 10x is going to be 10 times 0.666 repeating, and that's going to move all of these, so that moves it 1, they tell you. So that's going to equal 6.666 infinitely repeating, or 6.6 repeating. So 10x is 6.6 repeating. Now I have two numbers that have the same repeating part. So I'm going to line them up. 10x is 6.6 repeating, and x is just 0.6 repeating. If I line them up and subtract now, I see that this will infinitely many go away, and then I'm going to get 6 minus 0 is 6, equals 10 minus 1 is 9 x's. Solve for x. I'm going to get x is equal to 6 over 9, which is 2 times 3 over 3 times 3, cancel, which is 2/3. So 0.6 repeating is the fraction 2/3 in lowest form. Again, the idea here is we're going to take a number that has a repeating expansion, create two numbers that have the same repeating expansion, subtract them to get rid of the repeating expansion, and then solve for x. Now let's see how to find the decimal expansion of one kind of number, namely the square root of non-perfect squares. Okay, theorem 3 we're going to have is, first of all, let n be a non-perfect square. So perfect squares are 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. So 1, 4, 9, 25, all these numbers, 16, all these numbers are perfect squares. If you're not a perfect square, then the square root of that number, which is not a perfect square, is always irrational. What we're going to do now is, how do I find the decimal expansion? I needed some irrational numbers, first of all. So pi is irrational, you can prove, which is much harder. You can prove that e in calculus is irrational. You can prove that these guys are irrational, and any actual non-perfect nth power, the nth root of that is always going to be an irrational number. So we get whole categories of irrational numbers. And now I want to know how do I know that square root of 2, when you put that in your calculator, that you're going to get 1.414213 ... How does it know that? I'm going to try by hand. I'm not going to try, do or do not, says Yoda. I'm going to approximate the square root of 2, correct at 3 places, using a technique due to the ancient Babylonians in Mesopotamia several thousand years ago. How do I do that? First of all, what we're going to do is step 0, or we need an initial guess. This is going to be successive rational approximation. What we want to do is find out on this real number line now, how did I know it was going to be here? How do we know it's between 1 and 2? I've already drawn this and I showed you where pi was. What we do with the real number line is you draw a straight line, you indicate where 0 is, and then that's where negatives are going to be that way, which wasn't important for us because we've got a positive number. And then we're going to mark off unit lengths of integers, and then in between all of those things you can have some of the fractions, and that's where they're going to go. And we want to know on this line, where's root 2, or specifically what's his decimal expansion. So the first thing I'm going to do is find perfect squares on either side of 2. 4 is a perfect square and 1 is a perfect square. Now if I square root both of those, or all of these, then what I'm going to get is the square root of 1 squared is 1, is less than the square root of 2, is less than the square root of 4, which is also 2. So I now get the fact that I know that my irrational number is between 1 and 2. What does that really tell me? That already tells me that the square root of 2 is approximately equal to 1.C1, C2, C3, ... We want corrected the first 3 decimal places. So we already know that the units, or the 1 spot, or the integer part of that is going to be a 1. So it's going to be 1 point something from our initial guess. Now what are we going to do? Now we're going to use an iteration of the average, or the midpoint of the interval between 1 and 2 is always the average of the 2 endpoints. So if I do 1 plus 2 divided by 2 is going to be 3 over 2. And that gets me closer to my value than either of these original guesses. I know it's somewhere between 1 and 2, but if I look at the midpoint, that has to be somehow closer to than either of these guys to that, and then I can get closer and closer and closer. Let's do that. I'll erase and move everything up, and then let's do some iterated steps of how to calculate square root of 2. Here's the interval 1, 2. I've written it really big, and what we're going to do is take the average 3 over 2, and we're going to get new guesses, and what we're going to do is we're going to squish and squish and get closer and closer to this approximation of the square root of 2. So step 1, what we're going to do, we're going to create so first of all, in our first step, our initial guesses are step 0 as our initial guesses. X0 is 1 and Y0 is 2. And then we're going to create in each step. In the first step, we're going to create an X1 and a Y1. In the second step, we're going to create an X2 and a Y2. And what we're doing every time is we're guessing that XK times YK is equal to N, which means that they're approximately equal to, is what we're guessing. And if that's true, then that means that xk is approximately equal to the square root of n, and yk is approximately equal to the square root of n. In each case, you'll get an over and an under estimate because neither of them are going to be exactly the square root of 2 or n, but in each case, this is how we're going to get our guesses. So the new guesses, we're going to use this definition and our averaging business to get a new guess in each step, which will be better than the previous guesses, and then we can get closer and closer to the actual value or an approximate value of the square root of 2. How do I do that? X1 is going to be always averages. So the x's are always average of the previous guess. So this is the average of the previous guess, which in our case is 1 plus 2 over 2, which was exactly 3 over 2. So now this is X1. The midway point. It gets us closer to wherever the square root of 2 is. It's right in the middle of these guesses. My y1 is always going to be n over x1, which we just calculated. What's our n in this case? N is 2. I'm trying to find the square root of 2. So this will be 2 over 3 over 2, which is equal to 2 over 1 times 2 over 3, which gives me 4/3. So 4/3, not the scale, but let's put that there. 1.3 repeating. That's going to be my y1. And notice again, that says that it's going to be somewhere between there. You don't have to write this in every step, but what that says now is y1, which is 4 over 3, is strictly less than the square root of 2, is strictly less than 3 over 2, which is equal to x1. So it flips as we go who's the over and under estimate, but in each case I get one of the numbers that's slightly less than my number and one that's larger than my number. To get closer, what we're going to do is step 2. We're going to guess x2 is always the average of the previous guesses. So that's going to be x1 plus y1 over 2, which in our case now was 3 over 2 plus 4 over 3 over 2, which is simplifying. That'll be 1/2 times, I have to multiply this by 3 over 2. I'm missing 3 over 3 plus 4 over 3. I'm missing 2, so I multiply by 1 to get my common denominator. Now that's going to give me 1/2 times 9 plus 8 over 6, which is 17 over 12. Once I have that, my y2 is always n over x2, which is 2 over 17 over 12, which is 2 over 1 times 12 over 17, which is 24 over 17. So what we did was this last one, x2, which was the average, is going to be right in the middle of these ones. 17 over 12, and then the other one, 24 over 17, is going to go there, and that will be our y2. They're going to get closer. I won't draw the last ones. We're going to do one more step, I believe, and then that will give us, I'm pretty sure for sure, correct to 3 decimal places, 1.414 for our decimal expansion. Let's move that up. So step 3, x3 is x2 plus y2 over 2, the average of the previous guesses. This was 17 over 12 plus 24 over 17 over 2, which is 1/2 times 17 times 12, I need to multiply by 17, and 17 plus 24 over 17 times 12 over 12, which is going to give me 1/2 times 289 is 17 squared plus 288 over the common denominator. If I don't know, multiply 17 and 12, multiply these out, I'm going to get 14, I will get 8, I get 0, 2, 1, I will get 4, 0, 204. And so what that gives me is, oh, and then I need this one. If I have 289 and 288, this is going to give me 17. This will give me 17, 5. This will be 577, and then I'm going to get 408. So hand calculations. We don't need, where we're going, we don't need calculators. We are the calculator. So y3 is going to be equal to, but I'll probably use this one anyways. Y3 is going to be n over x3, which is 2 over 577 over 408, which is equal to 2 over 1 times 408 over 577, which is 816 over 577. These are the last two guesses that we got, which are going to now, remember, this will be the average right in between here, and then we have another guess, but we're getting pretty dang close. Now what do? We have a method of using rational numbers and having a method called long division to find their decimal expansion, which is approximately equal to the decimal expansion of root 2. Let's do that. I'll do this for x3, I'll do the long division, not both of them. I'm done with the video. First of all, what do? I have to divide this out. How do I do this? I want correct at 3 decimal places, so this is going to be 577.000. I want to, you can keep going, but we want to correct at 3 decimal places. What I'm going to do, obviously, now is list the multiples of 408. So the easiest way to do that when they're bigger numbers is add it to itself. So I'm going to get 816 times 2. 408 will give me 14,212,224 times 3. 408 will give me 12,361,1632 times 4. And then I'm cheating because I know it's 1.414, but one more, we'll get 10, 4, 20, 40 times 5. You list the multiples of the number first, then when I divide 408 into 577, it becomes a whole lot easier. How many times does 408 go into 577? 1. We should know that anyways because we already know from the very first step it was 1 point something. So what we're going to get is subtract. I'm going to borrow 17, 9, 6, 1. 1690 I get now. 1690 I see, oh, this will be a 4. And I'm going to get 1632. So I subtract, I get 8, 10, 8, 5, 580. I look at 580. Oh, again, what I'm going to get is a 1. I'm going to have 408. Again, subtract, borrow. This is going to give me a 2, a 7, and a 1. I'll bring this down. 1720. Still 5 is too much, so it has to be a 4. And then I'm going to get 1632, subtract, blah, 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 blah. All they wanted was the 3 decimal places. What this really tells me, therefore, is the square root of 2 is approximately equal to x3, which was 577 over 408, which is approximately equal to 1.414, correct to 3 decimal places. 4142130 something, I think, blah, 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 blah. This is how we approximate at least the non-perfect squares square roots. So some of the categories of irrational numbers, this is at least a method to approximate by hand their approximate decimal expansion. Please subscribe right here. I'll see you next time.